For all of you attending my talk. My name is Xinwei Fu. I have just graduated from Virginia Tech with a PhD degree. Today I will present Durinn Adversarial memory and thread interleaving for detecting durable linearizability bugs. And this is a joint work with Dr. Dongyoon Lee and Dr. Changwoo. Let me briefly introduce the summary first. Non-volatile main memory has arrived. It provides a new opportunity to build crash-consistent software without paying storage stack overhead. However, writing crash-consistent program is error-prone. And durable linearizability is used for determining whether a crash state is consistent or not. And this work proposed Durinn, the first durable linearizability checker designed for concurrent NVM data structures. And we present 3 durable linearizability bug patterns, and we propose adversarial crash state and thread interleaving construction and the likely-linearization point inference to allow Durinn to detect the DL bugs in an active and scalable manner. Durinn reports 27 bugs, and 15 of them are new and outperformed the state of art. This slide shows the outline of this talk, and let's go to the introduction first. Durable linearizability is used for determining whether a crash state is consistent or not. And now we are going to present the definition of durable linearizability. Durable linearizability requires 3 conditions. The first condition is that without a crash, all operations are linearizable. And linearizability is the existing widely used correctness standard for concurrent programs. And the linearization requires that all operations first take effect instantaneously at a program point, which is called the linearization point. And the second, that point is between the operation begin and end. Let's take an example here. For example, thread 1 is executing 2 continuous operations, and thread 2 is running a get operation concurrently. Under linearizability, the effect of operation must be taken between the operation begin and the end. So the get must observe the effect of the first insert, but the get may or may not observe the effect of the second insert. If the get does not observe the effect of the second insert, which means the linearization point happens earlier, then the get returns V1. If the get does observe the effect of the second insert, thus the linearization point happens later, and then the get returns V2. The second condition of durable linearizability, completed operation before a crash should preserve all semantic after that crash. And the all semantic means that the operation should be treated as fully executed after a crash. The last condition of durable linearizability, incompleted operation upon a crash should preserve all or nothing semantic after a crash. And the nothing semantic means that the operation should be treated as not at all executed after the crash. For example, thread 1 is executing 2 continuous insert operations, and the thread 2 is running a get operation concurrently. A crash happens at the second insert, which means the first insert is a completed operation, and the second insert is an incomplete operation. And under durable linearizability, there are 2 legal execution results here. First, if the get before the crash does not see the effect of the second insert, the get returns V1, which means the second insert is incomplete and should preserve all or nothing semantic. So the get after crash should return V1 or V2. And the second, if the get before the crash does see the effect of the second insert, which means the second insert is completed and should preserve all semantic. So the get after crash should return V2. In summary, durable linearizability describes the correct NVM operation behaviors in 2 dimensions. First, crash state, and the second, thread interleaving. And any incorrect operation behavior leads to durable linearizability bug. And let's use the previous example here again here. If the get does see the effect of the second operation, so it should preserve all semantic. So the get after crash should return V2. And this is one correct behavior. An incorrect behavior could be that the crashing insert fails to preserve the all semantic, then the get after crash return V1, and this is indeed a durable linearizability bug. This slide shows our contribution. Existing linearizability testing tools do not consider crash and recovery semantic, and NVM-specific crash consistency testing tool either require user-defined custom oracles or are limited to single-threaded NVM programs. And it is non-trivial to extend them for durable linearizability because testing space grows exponentially in 2 dimensions, crash states and thread interleaving. And this work proposed Durinn. We will present 3 durable linearizability bug patterns in the paper, and we propose adversary, crash state, and thread interleaving construction, and the likely linearization point inference to allow Durinn to detect those bugs. Now let's move to the Durinn part. I'm going to introduce the overview of Durinn first. The heuristic of Durinn is that once we know the linearization point, then we can understand the behavior of each operation. For example, what is the operation behavior if a crash happens before the linearization point, or between those 2 points, or after the durability point. And the design of Durinn is based on 2 key ideas. The first key idea is that by understanding the operation behavior under durable linearizability, Durinn classifies 3 bug patterns. And second key idea is that for each bug pattern, Durinn constructs a worst-case scenario to trigger incorrect behaviors. By constructing the worst-case scenario, Durinn only tests certain NVM accesses, thus further reducing the test space of crash states and also reducing the test space of thread interleaving in a unified manner. This figure shows the workflow of Durinn. Durinn takes a target NVM data structure and a test case as the inputs. Durinn first instruments are programmed. Program and runs a test case to collect a memory trace, and Durinn then infers likely linearization points from the trace. Given the trace and identify the LPs, Durinn performs adversarial tests to generate a collection of crashed NVM images and thread schedules. Lastly, Durinn validates the generated crashed NVM images along with the generated thread schedules to detect durable linearizability bugs. And today's talk focuses on the component of the likely linearization point inference and adversarial testing. Now I'm introducing the outline of Durinn. First, let's assume that we already know the linearization points, and we are going to present how to classify bug patterns and how to use adversarial testing. And we will present the likely linearization point inference later. Since the cache is still volatile, once an operation is visible, it doesn't mean it is durable. Linearization point is a program point where an operation takes effect and its effect becomes visible. For example, a cast to a token. Durability point is a program point where the effect becomes persisted. For example, in this figure, persisted token. The duration of an operation can be partitioned into 3 regions based on the linearization point and the durability point. And before the LP, which is the region 1 in this figure, the effect of an operation is neither visible nor durable. Between LP and the DP, which is the region 2 in this figure, the effect of an operation is visible but not durable yet. And after the durability point, which is the region 3 in this figure, the effect of an operation is both visible and also durable. And we derive 3 bug patterns based on where crash happens. And in this talk, we focus on the 3rd bug pattern in the paper. And the 3rd bug pattern is visible but not a durable bug, and we will call it DL3 bug for short. Under durable linearizability, if a crash occurs between linearization point and the durability point, and if the effect of the crashing operation has been already observed before the crashing operation should preserve all semantic. For example, thread 1 is executing an insert operation write key, write value, and write a token. And the write to the token is the linearization point, which makes the effect visible. Concurrently, there is a get operation, which observes the effect of the insert operation, so it returns value. And right after that, a crash happens. After recovery, thread 1 is executing a get operation again. And as the crash occurs between the linearization point and the durability point, the effect of the crashing operation has been already observed before crash. So the insert should preserve all semantic, and the correct return of the get after recovery should be the value. And the DL3 bug is triggered as follows. Suppose some or all of the writes before the crash are not persisted, and after recovery, the get cannot access the key and the value anymore, so the get returns none. And this behavior violates the correctness condition, since the insert should preserve all semantic. And now we are going to introduce the adversarial test for this DL3 bug. And what is adversarial test? Adversarial test is to construct the worst case scenario to increase the chance of triggering the bug. And let's have a look at the DL3 bug again. The right table shows all the possible crash states. Because the correctness condition is to preserve all semantic, which means every store is persisted. So adversarially, the worst case is every store is not persisted. And in this example, the worst case is that both key and value are not persisted. If there is a DL3 bug, the worst case will trigger it. And the DL3 bug is called visible but not durable bug because the effect of operation is visible before the crash but not durable after the crash. To trigger a DL3 bug, there are two requirements here. A pair of racy operation, just like the insert and get in this example. And the second, a specific thread interleaving shown in the figure. Durinn used a best effort solution to adversarial construct the thread interleaving. The first step is to find potentially racy operation in the single-threaded trace. And here we have a single-threaded trace, and we found a pair of potential racy operations. And second step is to generate the thread interleaving by using GDB breakpoints. And in this example, after executing the first 4 operations in a single-threaded manner to make the program reach a certain state, we let thread 1 run until reaching to the breakpoint of the store to the token. And then we let thread 2 run until it reached the breakpoint of the load of the token. Then we let thread 2 resume and inject a crash right after finishing its operation. And in this way, an adversary thread interleaving has been constructed to trigger the DL3 bug. We have just presented how to classify bug patterns and how to use adversarial testing to construct the worst case scenario for bug pattern. And those techniques assume that we already know the linearization point. And now we are going to present how to infer the likely linearization point from programmers. Durinn infers the likely linearization point by analyzing 3 concurrent NVM programming practices. The first practice is the atomic instruction. In log-free data structures, atomic instructions are typically used to update a synchronization variable and to make the effect of an operation atomically visible to other threads. Thus, Durinn identified atomic instructions as likely linearization points for log-free writer operations. Second, the second practice is guarded protection pattern. For example, a writer ensures that key and value are persisted before the token is updated. Also, a reader checks whether the flag is set before reading the key and value. The writing to the token is the writer's linearization point, since the change becomes visible after setting the flag. The last practice is the publish after initialization, which is an optimization to reduce the persistent overhead. It works as follows. First, allocating a new node, and then initializing the new node by setting key and value. At this moment, the new node is not visible yet. And finally, publishing the node by adding the node into the core structure, which is a linearization point that makes the new node visible. And based on this practice, we filter out all the stores to the newly allocated memory regions and exclude them from the likely linearization points. We have presented the key components of Durinn, and now we are moving to the evaluation. In our evaluation, we tested 13 concurrent NVM data structures, and the data structures are diverse. All tested data structures are highly optimized and use application-specific crash consistency mechanism, and it includes low-level persistent primitive and high-level transactions. The concurrency implementation includes both log-free and log-based. And we ran each experiment with 1,000 operations generated by AFL fuzzer, and the evaluation aimed to answer the following 3 questions. First, can Durinn detect new bugs? Second, how effective and how sound is Durinn's likely linearization point technique? And the third, does Durinn outperform the state of art? And we are going to answer those 3 questions one by one in the next 3 slides. The first question, can Durinn detect new bugs? In total, we detected 27 bugs from 12 data structures, and 15 bugs are new bugs. 7 of them have been confirmed by the developers, and there are 10 DL1 bugs, 7 DL2 bugs, and 10 DL3 bugs. And we also report the code location, description, impact, and fixing strategy for each bug. Second question, how effectively and how sound is the Durinn's likely linearization point technique? The number of the inferred LPs determine the number of the tests. More LP inferred leads to more tests, and any miss of a true linearization point may lead to missing a bug. To test the effectiveness and the soundness, we performed a detailed case study in which we manually analyzed the true linearization point for comparison. And the result shows that Durinn effectively reduced the number of likely LPs using 2 heuristics. Durinn only tests 35% and 82% of total stores, and the number of likely linearization points inferred by Durinn is twice as the number of the manually identified LPs. And importantly, our likely linearization points inference did not miss any true linearization points. The last question, does Durinn outperform the state of art? Now I'm going to present the detailed comparison with Witcher, the state of art, NVM crash consistency bug detector. Durinn detects all the bugs detected by Witcher in the common applications, and beyond them, Durinn reports 10 DL3 bugs that Witcher missed. This is because that Durinn reduced the test space of thread interleaving, while Witcher doesn't. We compared the number of tests performed by Durinn, Yacht, and Witcher over the same 1,000 operations. The x-axis is the number of operations, and the y-axis is the number of the tests. And the Yacht is an exhaustive testing tool, so the test space explodes within the first 10 operations. And the Witcher performs several times more tests than Durinn. And this is because that Witcher has to test every NVM accessory to explore all possible behaviors of one operation, while Durinn only adversarial tests worst case scenario based on durable linearizability. Let me conclude our work. This work proposed Durinn, the first durable linearizability checker designed for concurrent NVM data structure. We present 3 durable linearizability bug patterns. We propose adversarial crash state and thread interleaving construction, and the likely linearization point inference to allow Durinn to detect the DL bugs in an active and scalable manner. Durinn reports 27 bugs, and 15 of them are new and outperform the state of art. And thank you all. I'm ready for the questions.